Right. Thanks for the introduction. Right. Since this entire session is on backdoors, I guess I don't have to motivate backdoor too much. So I'll save the time for the real content of the talk. So the bit different from the earlier talk, this talk is more focusing on malware detection using ML models. And I'll explain to you why we are focusing on the malware detection. The main reason is our observation that many of the features on these malware take a very large range of values. So for example, some of them take all the way from 0 to 2 to the power of 32, for example. So these kind of unique features, when we are analyzing malware samples, would result in some very interesting things that I'm going to share with you in this talk. By the way, this is a joint work with a number of my collaborators from universities in China. All right, I guess I will skip this slide. All right, so we all know that ML is very useful in, for example, in the application domain of malware detection. And we also understand that many of the training data actually come from external parties, right? So, and that would actually lead us to this risk of backdoor attacks. So our main contribution in this talk, in this particular paper, is that we provide a new way of introducing clean label backdoor poisoning attacks. And we show you that we only need to inject a very small number of backdoor poisons in order to lead to a very substantial drop in the accuracy of the backdoor labels. I guess I'll also very quickly skip this one. All right, so compared to the very earlier work on this backdoor poisoning, our work focused on clean label poisoning, and we, as in the earlier talk as well, we also try our best to maintain the original functionality of the model that results from the backdoor. All right, so this is a very general workflow of the scenario, right? So we understand that the victim may actually obtain these samples, whether it's benign software or malicious software, typically from third-party agents. And that allows the attackers to potentially inject some of the backdoors into these training samples. And with these training samples, then the victim could potentially extract the features from the samples and then do the training, right? And that is what the attacker will do. They will submit so-called the crafted goodware, in our case, because these are clean label backdoor samples, right? So the adversary will inject this crafted goodware into the training sample. And after that, when the model has been trained, then it will result in the case where the watermarking malware would be considered as benign software, benign samples. So that is what we are trying to work on in such a setting. The threat model that we consider, the number one threat model that we will consider is so-called the unrestricted scenario, in which we assume that the adversary has complete knowledge on the training data as well as the model, right? So this is not a very realistic scenario. Of course, so we also consider other problem space constraints. So one particular application constraint here is that if you set a particular feature to a specific value, it may result in some conflicts in that particular sample. So we consider all these different constraints to make sure that the backdoor samples that we're injecting are realistic samples, would not result in a red flag. Right? We also consider these so-called data agnostic scenarios, where we assume that the adversary do not have access to the training set. So the adversary will have to use a different set in order to do the computation, as well as the data and model agnostic scenario, meaning that the victim may actually be using a completely different machine learning architecture from what the adversary is using. So later on, I'm going to show you the evaluation results under all these different settings. Now, first of all, let me explain the high-level idea of our work, and this is probably the most important slide that we want to explain here, right? So on the right-hand side, on the figures, you will see the blue color and the red color, and they represent the benign samples as well as the malicious samples. And we also draw the boundary that separates the two groups, right? So that is typically what the machine learning model is trying to do. Now, question we want to ask ourselves right now is, if we are the adversary, what kind of backdoor samples shall we use in order to have the biggest impact on the resulting machine learning model? So if you look at the top figure, right, that is idea number one, right? So that is the case where you introduce three. You can see the three benign backdoor samples that we introduced. Now, these three are probably not going to be very effective in order for us to push the machine learning boundary anywhere. The reason is because these three samples are so similar to the existing samples, right? So if you look at the x-axis, right, that represents one feature, y-axis represents another feature, for example. So in this particular case, it's very obvious that the x-axis is the one that is determining the machine learning boundary. And the three backdoor samples that we introduce here would not introduce any new knowledge for the machine learning to be learned. Right? So in this case, these are not a very good effective approach of introducing backdoors. Now let's look at the second figure now, right? The one in the middle, right? You can see that now the three backdoor samples that we're introducing are sort of like mingle within the malicious samples. Now, in order for the machine learning to be able to accommodate these three new backdoor samples, you can see that the boundary would have to be pushed a little bit. So in that sense, it actually works better than the graph on the top graph there. But at the same time, it's still not very effective. The reason is because, remember, the machine learning also has to cater for all the existing samples. It's not just to cater to that three new backdoor samples that we introduce. Right? So in this case, you can push the boundary a little bit, but not too much. Right? Now we consider the graph at the bottom, and that is what we are proposing over here. Right? You can see that the three new samples are introduced still on the malicious side. So in that sense, it's actually effective in pushing the boundary. But at the same time, if you look at the y-axis, okay, these three new samples, these three backdoor samples have a y-axis value that is very different from the original set of malicious samples, right? So originally, if you look at the original model, they are mainly using the x-axis as the main determining feature in order to do the clustering. But now with the three new samples introduced, the machine learning will realize that, hey, in fact, the y-axis is useful as well. So this is something that is very new that the machine learning is going to learn. And in order to do, and by doing so, the effectiveness of this backdoor injection will be a lot more than the other examples that we have above. So basically, the two main ideas that we're introducing in this paper is, number one, we need to use samples that are not so similar to the existing set of the benign samples, unlike the top graph. Top graph is so similar, not useful. Second thing we are trying to convince or argue is that we can use features that has a value that is actually not being characterized by the existing samples, right? So if the y value in this case usually falls into the middle, we're going to use some other y values that is actually not represented in the current set of samples. So these are two main ideas that we are introducing. And specifically, we have values, or we have the equations for us to capture these two important features. First one is on the p-value, and that is used to characterize the similarity of the samples. So p-value actually gives us a very good indication on the dissimilarity to the benign clusters. I'm going to skip the very detailed technical equations in terms of calculating the p-value, because this actually is not our contribution. It's actually in the literature, right? So we are using p-value to capture how similar the backdoor is compared to the existing cluster of the benign samples. And we are going to use this so-called variation ratio, something that we introduced in our paper, to capture where this new sample's feature value lies, right? So here I'm going to use an example to explain to you what this really means. So here in this particular case, you see that we have three features, feature 1, 2, and 3. And in this particular case, we are going to select the feature number 2 as our backdoor trigger. And the reason is because it is, has a lot it has a much higher dispersal level, right? So you can see that, okay, there are 9 samples falling into the lower value, 2 samples falling into the middle range, and then 1 sample falling into the upper range. So this one gives us a much better so-called dispersal level, and that would be giving us a lot more impact in the backdoor used. Right, so these are the 2 main metrics that we're introducing in order to introduce the effective backdoors. Right, so with this, I'm going to go to the evaluation of our work. Right, so we use 3 different data sets for our evaluation. One on Windows executables, one on Android executables, and one on PDF files. And this is the main experimental result. It shows you that compared to the existing approaches of introducing backdoor or clean label backdoor, our 2 measures, right? Remember, there are 2 measures. One is the p-value, and the other one is the variation ratio. These 2 new measures give us a lot more impact, a lot more effective in terms of the backdoors introduced. We can introduce only like 0.01% of the poisons, and that will lead us to all the watermarked sample being recognized wrongly. Right? I also briefly mentioned earlier that we have different constraints that we consider. So for example, this is the result of the so-called data agnostic scenario, in which we assume that the adversary only has access to his own set of samples, but not the actual training sample that the victim is using. And still, the 2 metrics that we propose is still a lot more effective compared to existing work. There are a lot more other evaluations that we consider. I'm not going into the details over here. You can always refer to our paper on these other scenarios. The last thing I want to show is, remember we talked about the p-value, which captures the similarity, right? So in this case, we see that a much higher p-value in fact hurts the backdoor effectiveness, right? So the more this kind of backdoors introduced, the worse or the not so effective of the backdoor. So in this case, it is much better for you to introduce a very small number of high quality backdoors compared to a large quantity of not so effective backdoors. Right. We also work on a lot of the mitigation techniques, and we find that they are actually not effective in detecting our backdoors. Right. And we also introduced this way of compressing the subspace. Remember, this vulnerability comes from the fact that the features takes a large range of the values. So if you can actually compress that large range of values into smaller buckets, that would be an effective countermeasure to this particular backdoor injection attack. Right, so with this, I'm going to conclude my talk, and I'll be happy to take questions if we still have time. Thank you.